Welcome back, class. In the last lesson, we introduced this idea that there exist certain families of linear equations. In particular, we saw that whenever you have a two-step LEOV, two-step linear equation of one variable, such as 5x plus 1 is equal to 10, you may reduce the two-step LEOV to a one-step LEOV by first removing the number that is being added or subtracted from your unknown terms. So in this case, we had a 5x plus 1 is equal to 10, and we saw that you could use the additive inverse to remove the 1 that's in front of your 5x. Once you have reduced your two-step LEOV to a one-step LEOV, depending on what type of one-step LEOV you're dealing with, in this case, for this problem, you have a multiplicative one-step LEOV, you can reduce that one-step LEOV by using either the additive or multiplicative inverse on both sides of your equation. In this instance, since we have a multiplicative one-step LEOV, we will use a multiplicative inverse of 5 to solve for our x value. The multiplicative inverse of 5 being 1/5. So when we multiplied 1/5 on both sides, we were able to find that x was equal to 9/5. Now we generalized the solution process for finding a solution for a two-step LEOV, and we saw that it really doesn't matter what number is in front of your unknown number, x. It doesn't matter what number is being added or subtracted to your unknown term, and it doesn't matter what number is on the other side of your equal sign. In this instance, for this two-step LEOV that you see in front of you, we have an a, b, and c that can be any real number that we choose. These could be fractions. These could be negative numbers. They could be regular positive integer values. It doesn't matter. They could even be decimals. But whatever number that we choose for a, b, and c, we can always solve a two-step LEOV using the following set or sequence of procedures. You first start by removing the b value that's in front of your ax term by adding the additive inverse of b to both sides. That then allows you to isolate your ax, and then, of course, you could use your multiplicative inverse on both sides of your equation to solve for x. We saw that even more complicated problems, such as multi-step LEOVs, follow a similar pattern. We're going to take a very complicated linear equation of one variable, and we're going to keep applying the rules of algebra over and over and over again, and eventually we'll be able to finesse the multi-step LEOV to a two-step LEOV. With the idea being that since we know how to solve for a two-step LEOV, we can quickly reduce the two-step LEOV to a one-step LEOV, and from a one-step LEOV, we'll find the solution. And that's going to be our general strategy for solving the problems that you see in section 2.3. Now, the problems in 2.3 can be categorized into a number of different types of multi-step LEOVs. The first type of multi-step LEOV, which I think is the easiest for students to understand, is what we call the collecting like terms multi-step LEOV problem statement. Now, a collecting like terms multi-step LEOV problem statement, we usually have the student try to manipulate an equation where you see multiple unknown values. In this case, for this equation, you've got a 5x plus 3x. And you have multiple numeric terms as well, such as the -5, the -15, and a 20 on the other side of your equal sign. Now, why we call these types of problems a multi-step LEOV collecting like term problem is because what you're going to have to do is you're actually going to have to collect like terms in order to solve this problem statement. You can, for example, add 5x plus 3x together. Well, if I have 5 apples and I add 3 apples to it, I'm going to get 8 apples. And similarly, we can take our -5 and -15, add those together. If I owe you $5 and then at a later point I owe you 15 more, I'm going to owe you $20 in total. And voila, we have transformed the collecting like terms problem to a two-step LEOV. From this stage, or at this point rather, it's going to be rather straightforward for us to solve the equation. We're going to add the additive inverse of a -20 to both sides of our equation. And what that's going to do for us is it's going to allow us to cancel out the negative 20 that's in front of my 8x. So I will then have 8x plus 0 is equal to 20 plus 20, which gives you 40. 8x plus 0 is just 8x, and I have 40 on the other side of my equation. Then we're going to multiply by 1 over 8 on both sides of our equation. Why 1 over 8? We're going to multiply by 1 over 8 because 1 over 8 is the multiplicative inverse of 8. And if we multiply by the multiplicative inverse, we can clear the number that is in front of our x. Okay, so 8 times 1 over 8 will give you 8 over 8, and 40 times 1 over 8 will give you 40 over 8. 8 divided by 8 is just 1, so you'll have 1 times x, and 40 divided by 8 is 5. 1 times x is just x, so now you have found that x is equal to 5. The next type of collecting like terms problem doesn't really appear at first to be a collecting like terms problem. In this particular case, you have a unknown variable term on the left, but you also have an unknown variable term on the right. The problem being that this is going to confuse a lot of students because you can't collect these like terms. They're not on the same side of an equal sign, which is usually what students are used to dealing with. So the challenge here is to understand that we, the reader, the person who's solving the problem, can decide what side of an equation we want to work with. Now, I'm probably going to try to work with a side of an equation where I'll have positive coefficients in front of my unknown terms. And so if I'm solving for p, I want to make sure that whether I'm working on the right side of my equation or on the left, I want to make sure the number in front of my p is not going to be negative. That's just a general rule. It's a good rule to stick by. But theoretically, you could work on any side of the equation. And just for the sake of example, I will show you that that is the case. So if I wanted to make sure that my p-value wasn't going to be negative, and I saw that there was this 10p right here, I might decide, well, I should probably move this 10p to the other side, from the left side to my right side. And how I can do that is by adding a negative 10p to both sides of my equation. Now for consistency, I'm going to add negative 10p on the left side of my equation. And you'll see that I've got a negative 10p plus 10p. That's going to give me 0p on the left-hand side, plus 15. And then on my right-hand side, I'll have negative 10p plus 20p. The way you should read this is you have $10 that you owe someone, but you deposit $20 in your bank account. When you get done paying back the debt, you should have $10 remaining. And the minus 5 doesn't change. The next step, we're going to carry this forward. We're going to look, we see a 0p. That's just 0. So you've got 0 plus 15 is equal to 10p minus 5. 15 plus 0 is just 15. Okay. Now we have a two-step LEOV. If we wanted to solve this problem, always remember that you're going to attack the number that's being added or subtracted from your unknown term. In this case, our unknown number is p, so we want to attack the negative 5 that's hanging out in front. We will add 5 to both sides because that's the additive inverse of a negative 5. So we'll have 15 plus 5, or 20. And then on the other side, we'll just get 0, because negative 5 plus 5, that gives us 0. Now we have 20 is equal to 10p. Now you've got a one-step LEOV. Okay, you're almost finished with the problem statement. Go ahead and use your multiplicative inverse to clear the number that's in front of your p. We're going to multiply by 1 over 10 on both sides, because 1 over 10 is the multiplicative inverse of 10. You'll get 10 over 10 p and 20 divided by 10. 10 divided by 10 gives you 1, so you'll have 1p is equal to 20 divided by 10, or 2. You'll just have p is equal to 2. And that's your answer. Now, as I told students, as long as we are following the rules of algebra, It really doesn't matter what side of the equation we decided to work with. We could have worked with the left side of the equation, or we could have worked with the right side of the equation. In the previous problem, I decided to move my 10p from the left to the right? So I was working on the right side of my equal sign to solve for p. But I could have just as easily used the other side of the equation, and I'll get the same value. So the student has to make this decision for themselves. I can't tell you in every single instance which side of the equation you should solve for. You have to develop that confidence enough in your own math and double check your work, triple check, quadruple check your work to make sure that you're doing it right. If I wanted to move the 20p from the right side to the left side, because you have a positive 20p here, I'm going to use the additive inverse of 20p, which would be to add a negative 20p to both sides of my equation. When I do that, I'll have negative 20p on the left side and negative 20p on the right side. On the right side, negative 20p plus 20p, that will be 0p, just because of the inverse law. So I'll have 0p minus 5. And on the left-hand side, I've got negative 20 plus 10p plus 15. Well, if I owe you $20, but I pay you back $10, I should still owe $10. So I'll have a negative 10p. And the 15 doesn't change. The final thing that we have to do is we need to move the negative 5 from the, well, rather, I guess we don't have to move the negative 5. We just have 0. P is going to be 0 minus 5. Yeah, we'll just leave the negative 5 on the right-hand side. But what we can do, if you guys are seeing this, is we now have a two-step LEOV. So because we have a two-step LEOV, now we can use our additive inverse on both sides of our equation. In this case, we'll use the additive inverse of the positive 15, which will be at negative 15. I'm going to add negative 15 to both sides of my equation because negative 15 is the opposite or the additive inverse of a positive 15. This will allow my 15s to add to 0. I'll be left with a negative 10p out in front and negative 5 plus a negative 15. That should give me a negative 20. Because if I owe you $5 and I owe you 15 more, I will owe you $20 in total. Negative 10p plus 0 is just negative 10p. Again, that's the additive identity. So I'll have negative 10p is equal to negative 20. Note that this is now a one-step LEOV. At this point, you can go ahead and multiply by negative 1 over 10 on both sides of your equation. You will have negative negative is a positive, 10 over 10p. Negative negative is a positive, 20 over 10. 10 divided by 10 gives you 1, so you'll have 1p on the left-hand side. 20 divided by 10 gives you 2. So we have arrived at our previous solution, p is equal to 2. Note that I'm not doing anything magical. As I'm working through this problem statement, I'm working one step at a time, sequentially, and I'm only using a single algebraic operation at a time. I'm not mixing and matching my multiplicative inverse. I'm not asking myself, oh, can I multiply now? Can I divide now? No. You only have two options. You're either going to use the additive inverse or a multiplicative inverse 9 times out of 10. Unless you have a distribution problem case, you're only going to want to focus on those two main operations. Which brings us to the distribution problem case. Now, the distribution problem case is going to be the other category of problem type that you encounter with multi-step LEOVs. Now, the good news about a distribution problem case is that these are easy to spot. The distribution problem case will always have a sequence of parentheses and some sort of a number that's being multiplied by a sequence of terms that are inside of the parentheses. In this instance, you've got a 5 that's hanging out in front of a y minus 2. So using the distribution law, if we go back to our rules of algebra, we know that if we have any number sticking out in front of a sequence of parentheses where the terms are being added or subtracted from each other, then it's like you take the number and you're going to multiply across the values that are inside of the parentheses. And so for this particular equation, what we're going to do is we're going to take our 5 and we'll multiply by the y, and we'll take our 5 and we'll multiply by a -2. Note that even though my y is actually subtracting 2, or rather 2 is being subtracted from y, I'm not going to write the subtraction symbol here. I'm going to instead treat this this 2 being subtracted from y as though it is a -2. The reason why I'm going to do that is because it's going to help you keep your negative symbol straight. You got to trust me on this, okay? It's very easy to get confused if you have a bunch of negative numbers all multiplying with each other, and you might lose track of your negative symbol at that point. But if we've done this correctly, we should now have cleared our parentheses, and you'll see that, well, 5 times y just gives you 5y, because essentially we don't know what the y is, so it just means an unknown number. So you're now just saying you have 5 sets of an unknown number. There's not much we can do with that. But for this second term, you've got a positive and a negative, which is a negative, and 5 times 2, which gives you 10. On the other side of the equation, you don't really have to bother with it. 10 is just 10. You now have a 2-step LEOV. Brilliant. Once you have a 2-step LEOV, you just need to use your additive inverse on both sides of the equal sign. In this case, your additive inverse of a -10 will be a +10. By adding 10 to both sides, you will have a 5y plus 0 is equal to 10 plus 10 gives you 20. 5y plus 0 just gives you 5y. You now have a 1-step LEOV. Go ahead and use your multiplicative inverse to clear the 1-step LEOV multiplicative case. You'll have 5 over 5y is equal to 20 over 5. 5 divided by 5 is 1. 20 divided by 5 is 4. Y is equal to 4. And that is your answer. Okay, so not too much trouble. There are a decent number of steps. These problems are going to be a little bit more involved than probably what you were used to in your other classes. But it's not too bad. It's not, basically all we're doing, if you guys think about it, is apart from just having to memorize that you've got an additive inverse and a multiplicative inverse. That's really the only new concept that we're dealing with in this problem statement, in addition to distribution law. Okay, distribution law too. But apart from those 3 things, all you're really doing is you're doing addition and multiplication, right? Like this -10 plus 10, that was just an addition operation. The 5 times the -2, that was a multiplication operation. The 1/5 times 5, y, that was a multiplication operation. Okay, and then finally you had a 20 divided by 5. That was a division operation. So the long and the short of it is, gang, if you really focus on building up those skills of doing addition, subtraction, multiplication, and division really, really well, you're going to not have as many problems with these problems. You're not going to have as many issues with these problems, rather, as you might first believe. They're a little bit tricky to get the hang of because we have to develop the confidence that our answers are correct. But once you do develop the confidence, you're going to be set. Moving on to a more challenging distribution problem that is actually a combination case. This type of problem is going to combine both the distribution law style of solving a problem statement as well as collecting like terms. First off, because you have a sequence of parentheses, you can go ahead and use the distribution law. Should have 3 times z plus 3 times 1. You'll have 2 times z plus 2 times, and I'll write the -3 as a -3 inside parentheses. I want you guys to notice that as I'm going along, I'm not performing the multiplication operations. I'm being very careful to just do an accounting step. All I want to do is I want to write down what numbers I'm working with. And then in my next step, what I'm going to do is I'm going to scan through this. We'll clean up the negative signs if there are any negative signs. And then I'll also go ahead and do the multiplication. 3z, that's just 3 times an unknown number. 3 times 1 gives you 3. 2 times z is just 2z. Positive, negative is a negative. 2 times 3 is 6 plus z. There's a reason why I'm working through the problem this way. It's gonna allow you to be able to obtain a more accurate answer with less mistakes, hopefully. Now we have a couple of options. We can decide if we want to work on the left-hand side or the right-hand side. In this instance, it may even be the case that we'll get a problem that has no solution. It's sometimes the case with these distribution style problems, you may not have a solution to your linear equation. It may be the case that, in fact, the equation is not balanced to begin with. It's a bunch of nonsense. And so since the equation is a bunch of nonsense, when you actually go to solve it, you're going to get nonsense. Now, at this step here, you'll note that you've got a 2z and a z. All I'm going to do is I'm going to use that commutative law. Note that you can pull your terms forward or backwards, wherever you want to pull them, so long as there's a sequence of addition steps and we remember to move the symbols that are attached to numbers as well. So if you have a negative number, when you pull that number forward, you have to remember it's still a negative number. So if I pull, say, this z forward and park it next to the 2z so that I have 2z plus z, it's not 2z minus z, it'll be 2z plus z, and then my minus 6 is still hanging out in front. Okay, so you just have to be careful about that. Now, if we do that, we now have 2z plus z, which gives me 3z. So we'll have 3z minus 6 on the right-hand side and 3z plus 3 on the left-hand side. Now, in this particular instance, what's going to happen is, regardless of what direction you wanted to pull your 3z, if you wanted to pull it to the left-hand side or the right-hand side, as soon as you use an additive inverse, i.e. add a negative 3z to both sides, your 3z on the left-hand side is going to cancel out. You'll have 0z, because if I owe you $3, but I add $3 to my bank account and I pay you back, I'll have $0 in my bank account. So I'll have 0z plus 3 on the left-hand side. On the right-hand side, it's going to be very similar. You're going to get 0z minus 6. But here's the weird thing. You'll have 0 plus 3 is equal to 0 minus 6, or 3 is equal to negative 6. And a student would be rightly confused. This is a nonsense answer. And what it means is that the equation was unbalanced from the get-go, and there's no solution. No solution. You might have a circle with a little diagonal dash to denote that there is no solution to this problem statement. Just watch out for that instance where there might not be a solution. The last type of distribution problem that I want students to be aware of is what I call the Hindu-Arabic style problem. Now, it turns out that if you read these ancient manuscripts that discuss various math topics from the 7th and 8th and 9th century, that the ancients really didn't like dealing with fractions. And whenever they encountered fractions, especially fractions that were in algebraic equations, they had a special technique that they would always utilize over and over and over again to essentially finesse their equation so that they weren't dealing with a bunch of fractions. The equation that you see here is one such situation where we might want to try using the Hindu-Arabic technique. Now, all you have to do for the Hindu-Arabic technique is you take note of whatever number happens to be in the denominator of your fractions. If you had multiple fractions, you would have to take the least common multiple of all of those numbers. In this instance, since we're only dealing with one fraction, what we're going to do is we're going to take this denominator, and what we're going to do with the denominator is we're going to actually multiply the denominator across this entire equation. Note that we could do this because this is the multiplicative property of equations. We can multiply a value on both sides of our equation while preserving the quality of the equation itself, i.e. will preserve the values of our unknown number, which is k in this instance. So if we're going to solve for k, we'll multiply through by this denominator 3. And what that's going to do for us is you should know that this 4 times 7 minus k could actually be written 4 over 3 times 7 minus k. So when we multiply the 3 across everything, you're going to have 3 times 4/3 times 7 minus k on the left-hand side, and you'll have 3 times k on the right-hand side. Don't forget that you can rewrite nasty-looking fractions such as this as a fraction multiplication problem, because what you're doing is you're essentially exploiting this rule of composite fractions, where if you have, say, two numbers in your numerator, you can break open your numerator and write the number out in front of the fraction, because in this instance, a times c over b would be the same thing as a over b times c over 1, and c over 1 is just c. So what we had here, this would have been our a value if you want to play pretend. This 3 would have been our b value, and this 7 minus k would have been the c value of this composite fraction down below. And incidentally, or as a consequence, we can then break up the fraction, and you'll have 4/3 parked down in front of your 7 minus k. And then because we're multiplying both sides of our equation, what's going to then happen is 3 times 4 gives you 12. You'll have 12 over 3. And that doesn't seem as helpful at the moment, but 12 over 3, well, 12 divides 3. 12 divided by 3 gives you 4. And in fact, in the ancient manuscripts, they would skip this step. They would just assume that you could follow the math. They would say, well, 3 times 4/3, the 3's will cancel out, it's leaving you the 4. But this is really what's happening, is that they're taking the 3, multiplying by 4, giving you 12, then dividing by 3, that gives you 4. Okay, whatever the case is, as long as you can follow the math, everything's fine. Just do things in a way to where you're consistent and you're not confusing yourself. So if you have to write everything out just so that you don't confuse yourself, go ahead and feel free to do so. At this step, you have a normal distribution style problem. You're going to take your 4, multiply by the 7, take your 4, multiply by your negative k. 4 times 7 gives you 28. Positive, negative is negative. 4 times k gives you 4k. And at this stage in the game, you can just add 4k to both sides. We'll have 28 plus 0 is equal to 7k. 28 is equal to 7k, and you're at a one-step LEOV. Use your multiplicative inverse of 7, which is 1 over 7, and multiply by both sides of the equation. 7 times 1 over 7 just gives you 1. You'll be left with k. 28 times 1 over 7, that'll give you 28 over 7. 28 divided by 7 gives you 4. So your k will equal 4. And that's pretty much all there is to this type of problem. Now, in a more complicated example, such as problem 74 from your textbook, you've got 2x plus x plus 3 all over 12 is equal to 3x plus 1 all over 4. This problem can also be solved using the Hindu-Arabic method. The only thing that you have to account for is you have to, instead of just multiplying through by a single number, you're going to multiply through by the LCM, the least common multiple of your denominator. It turns out that the least common multiple of 3, 4, and 12 is going to equal 12. You can always find your least common multiple by doing prime factorization. If you guys forgot, you'll do prime factorization. 3 is already a prime number. And 4, it can be just written as 2 times 2 if you want to. And what you do with the prime factorization is that the prime factorization is going to tell you what terms you need to add to all of the numbers in order to find a common multiple. Now, you'll note that you have a 2 and a 2 in front of this 3. And there's a 2 and a 2 here. You have a 3 here. There's a 3 here. So what it's telling you is you needed to add a 2 and a 2 to this 3. You needed to add a 3 to this 4. And you would be able to have an LCM, or force an LCM to exist. Or said another way, the LCM of 3, 12, and 4 happens to be 12. So if you had taken 12 and you multiply through this entire equation, you have to be a little bit careful with how you write this because it's going to look like a mess. But if we're careful, we're going to get the following. You'll have 12 times 2/3 x plus 12 times x plus 3 over 12 is equal to 12 times 3x plus 1 all over 4. Now, the magical thing at this part of the equation, or this part of the process, rather, is that your 12 will divide out by whatever's in your denominator. So for this first fraction, 12 divided by 3 gives you 4. So you can write 4 times 2 times x. For this second part of your equation, you've got 12 divided by 12. Well, 12 divided by 12 is just 1. So you've got 1 times whatever is remaining, which is x plus 3. And then for this right-hand side of your equal sign, you've got 12 divided by 4, which gives you 3. And the 3x plus 1 is remaining. Okay, 4 times 2 gives you 8, so you'll have 8x. 1 times x plus 3 just is x plus 3. And you have 3 times 3x plus 1. You'll see that I've reduced this nasty-looking equation to what is now effectively just a distribution and collection style problem. We can use the distribution law on the right-hand side of our equal sign. We can remove the parentheses from the x plus 3 using the associative law. We can collect our terms together. 8x plus x gives us 9x. 3 times 3 is 9. 3 times 1 is 3. In this problem statement, you will encounter another interesting result, which is if you try to use an additive inverse to collect your 9x's rather, together. If I use the additive inverse of a positive 9x, which is a negative 9x, and I add it to both sides of my equal sign, my 9x will cancel out on the left. My 9x on the right will also cancel out. So you'll have 0x plus 3 is equal to 0x plus 3. And 0x is just 0. 0 plus 3 gives you 3. So what's going to happen is you have 3 is equal to 3, which is just true. What this is telling you is you have infinite solutions. And what that means in practice is that you could have plugged any value, any real number in for x for this entire equation, and you would get a true answer, meaning that whatever is written on the right-hand side and whatever is written on the left-hand side are actually equal to each other, just in a different form. And so it didn't matter what value of x you picked, you would have an equation that remains in balance. You only have the illusion that the left and the right-hand side of your equal sign are out of balance because you've got these different fraction terms on the left-hand side. But if you had combined your fractions together, which would be a little bit challenging perhaps, but if you had done that, you would see that the left-hand side and the right-hand side were actually equal to each other. And thus, because both sides were equal to each other, there's an infinite number of solutions for x. That's all we have for section 2.3. I'll see you guys in class.